We are now going to start the fourth section of this chapter, and this is the last section. It's named the Diophantine equation. Ax plus by equal to c, where a, b and c are integers. So we are now going to see what this equation is all about. But before we jump into the actual theory, the section itself starts off with a little history. So let us also see what the author has to say. So that in the beginning itself, the name honors the mathematician Diophantus, because after him only this equation of course is not a single equation. You already can see, if you change these integers a, b and c, the equation changes. There will be infinitely many such equations, but all of these equations are called Diophantine equation. Collectively they are called Diophantine equations, and the name honors the mathematician Diophantus, who initiated the study of such equations. So he was the first who systematically studied this type of equations. But who was Diophantus? Unfortunately, practically nothing is known about Diophantus as an individual, save that he lived in Alexandria sometime around 250 AD. This much is known. He lived in Alexandria around 250 AD. The only positive evidence as to the date of his activity is that the bishop of Laodicea, who began his episcopate in 270, dedicated a book on Egyptian computations to his friend Diophantus. Now this place Laodicea or Laodicea, I don't really know how to pronounce it. Maybe it's Laodicea or Laodicea. Whatever the pronunciation is, this place is in modern day Turkey. So the bishop of Laodicea dedicated a book. Probably he himself wrote the book, I don't know, or nothing is written here about that, on Egyptian computations to his friend Diophantus. So from this information we get to know that Diophantus was friends with the bishop of Laodicea, and these things are way back in those days, very long ago. Although Diophantus's works were written in Greek and he displayed the Greek genius for the Oriental abstraction, he was most likely a Hellenized Babylonian. So all his works were written in Greek and he displayed the Greek genius for Oriental abstraction. Oriental means things related to Asia, things originating from Asia, Asian culture, Asian science, things like that. So Greeks used to study such things. Diophantus himself had a genius for such things. But in spite of all these things, he was most likely primarily a Babylonian, but Hellenized Babylonian. That means Hellenized means he adopted Greek things, Greek culture, Greek language. Then the author writes, okay, this next part is very interesting. The absolute personal information, whatever little we know about Diophantus, next comes in this strange form. It comes from the wording of an epigram problem which apparently dates from the 4th century, so long ago. And the problem, although it's not really a problem, it's more like a piece of information. It says his boyhood lasted 1/6 of his life. So 1/6 of his life was his boyhood. His beard grew after 1/12 more. But it sounds very strange, but it is what it is. It's given like that. His beard grew after 1/12 more. After 1/7 more he married, and his son was born 5 years later, 5 years after his marriage. The son lived to half his father's age, and the father died 4 years after his son. So if this entire thing is expressed in the form of an equation, it would look like this. Let Diophantus lived for x years, then 1/6 of x was his boyhood. Then after 1/12 more, his beard starts to grow. So at this point his beard starts to grow. After 1/7 more, he gets married. So at this point he marries. Then after 5 years of marriage, his son is born. Then the son starts to live, but he unfortunately lives only half of his father's life in terms of time. So plus 1/2 of x. So his son dies at this stage. But Diophantus himself lives for 4 more years. So plus 4, and then he also dies. So that is his entire life x. Now if this equation is solved, one gets the value x equal to 84. Now of course this information, I mean this little pieces that 1/6 is his boyhood, this is obviously not accurate. All these are most likely cases resulting in this value itself not being accurate. But we can say that more or less he lived for 84 years. But in what year or even in what century, that is unknown. Okay, that is unknown means uncertain. Okay, now the works of Diophantus. The great work upon which the reputation of Diophantus rests is his Arithmetica. And this Arithmetica is the earliest treatise in which may be described as the earliest treatise on algebra. Only 6 books out of the original 13 have been able to be preserved. Okay, so he wrote 13, but only 6 books have been able to be preserved. And in this Arithmetica, we see the systematic use of mathematical notations for the very first time. Although the signs, for example, here we have used mathematical notation. All these things, just like how I said, those pieces of information, that is, he lived for his boyhood lasted 1/6 of his life. So all this entire thing can be, of course, written in words as a sentence. However, to shorten things and to make things more compact, we use notation. So he was the first to systematically use such notations in Arithmetica. But the notations were really not these extremely compact symbols that we use today. I mean, in the sense that we use these symbols today, but more like abbreviations for words. For example, instead of writing this plus symbol to denote addition, Diophantus would have written ADD, something like that, an abbreviation, or say AD to denote addition. You should appreciate that he was the first one to do such things and to recognize that this type of things would make life easy. I mean, you can imagine that how much information is contained in this single equation, as opposed to this, if we have to write it entirely in words, we have to write long sentences. So that's that, and so that's what the author is saying. Although the signs employed are of the nature of abbreviations for words rather than algebraic symbols in the sense with which we use them today, special symbols were used to represent frequently occurring concepts such as the unknown quantity in an equation. We use letters x, y, z today, but he also used some symbols for the unknown, and in fact different powers of the unknowns up to the 6th power. Okay, so such things he did, and Diophantus had a symbol to express subtraction and one for equality. So these things he had, he did all these things in Arithmetica. Now it is customary to apply the term Diophantine equation to any equation actually in one or more unknowns, but there is a condition that is to be solved in the integers. So what this line means is that, for example, you have an equation like this, say 2x equal to 3, an absolutely easy, extremely easy, almost trivial algebraic equation in which x is the unknown. Now if you think of this equation as an equation in which you are having ingredients from the system of real numbers, that is 2 and 3, these are real numbers, then the equation has this unique solution 3 divided by 2, which if you express in decimal system, it looks like this 1.5, and which in fact actually is rational. But if I say Diophantine equation 2x equal to 3, then that means that this equation has to be solved in the integers, which in turn means that we seek an integer x for which 2x equal to 3, which however does not exist. We can clearly see. You do not in fact have to go through this type of reasoning to asserting that this has no integer solution. You just go by contradiction. You assume that there is an integer x for which 2x equal to 3, but then the left hand side is an even integer, but the right hand side is an odd integer, and no even integer is equal to any odd integer, so no solution exists. So if simply this equation is given and we are asked to find a solution in the system of real numbers, this is a solution, and in fact it's the unique solution. But when we say Diophantine equation, then this equation has no solution. However, still keep in mind what is written here. Any equation, it is customary to apply the term Diophantine equation to any equation in one or more unknowns, any number of unknowns, but the solution is to be found in the system of integers. That's the point. You can in fact have pretty complicated equations also, where you can seek integral solutions. For example, things like this. Say I throw in another variable, say 14, and then I ask, is there any integers x and y for which this has a solution? The situation becomes quite complicated. So the study of Diophantine equations is not trivial in any sense. Here of course it is trivial because we have only one variable, and that too only the first power of the variable is appearing, but in general anything can happen. Here however we are going to consider only linear Diophantine equations, that is in which the unknowns are occurring only in their first power. x by, no x square by cube or something like that, or cross terms like xy square. Such things we won't have. Only this, but to have the equation absolutely not trivial like this, we have two unknowns. Okay, so in that sense, the simplest non-trivial Diophantine equation. Now, what does it mean to solve this? It just simply means this. It just means to have two integers x0 and y0, which if you substitute for x and y respectively, then the equation is satisfied. That is, ax0 plus by0 becomes equal to c. So when we are writing something like this, the Diophantine equation, solve the Diophantine equation, say 2x plus 5y equal to 6, then the word integers will not be mentioned. It's understood that we have to find integer solutions. That's why Diophantine equation. Now, curiously enough, the linear equation, that is this type of Diophantine equations, actually does not occur in the works of Diophantus. Does not appear in the extant works of Diophantus, that is those 6 books which have been able to be preserved. This linear case does not occur there. The theory required for the solution to the linear case is to be found in Euclid's Elements, possibly because Diophantus himself viewed the linear case as trivial. Instead, most of his problems deal with finding squares and cubes with certain properties. Okay, so he ignored the linear case with the view that it would be trivial. Now, a given Diophantine equation, I am writing all these things in quite a haphazard manner because we have still not started the things properly. Okay, but perhaps I should now start writing. No? That's just all about the history. So let us now start writing things systematically. That's all about history means that's all we have in this text about the history. Mathematical history is extremely, just like general history, interesting, and there are so many things. This is of course really not all that we can say about Diophantus and his history. Definitely there will be more, but here however it's just a little about him, just to start the section off. A given Diophantine equation can have many solutions. For example, the Diophantine equation this one, 3x plus 6y equal to 18 has the solutions three times 4 plus 6 times 1, 12 plus 6 is 18, but also 3 times minus 6 plus 6 times 6 is 18, and also there is another one, 3 times 10 plus 6 times, so this should be minus 2, is also 18. In fact, there are others also. So these three have been shown just to show that such a Diophantine equation actually can have more than one solution. As opposed to this, the okay, let me just see whether these things are really what the author is claiming them to be. You see, no matter how reputed a book is, or how big of a mathematician someone is, or what their reputation is, you should always look at everything from a student's point of view. Anything may have mistakes. In fact, the authors themselves say or write in the preface that any mistakes that still after going through the drafts and after going through things, rectifying things many times, still mistakes may be there. Okay, so we have to keep an eye out for those mistakes. So it does not matter how nicely something is written in a book, we should really see whether it's true or not. There is no problem with this one, because 12 plus 6 is 18, minus 18 plus 36 is 18. Or if you take 6 common out, then inside you have, the other factor is 6 minus 3, which is 3. That 3 times 6 is still 18. 30 minus 12 is 18. Yeah, fine. As opposed to this, so this one has more than one solution. As opposed to this, the Diophantine equation (2x plus 10y equal to 17) has no solution. No solution means, of course, no solution in the system of integers. If you relax that condition, in the system of real numbers, of course, it has a solution. It has, for example, it will have more than one solution. One of them is 17 divided by 2, which is x, and you can take y to be equal to 0. Another easy solution would be when you take x equal to 0 and y equal to 17 divided by 10. But these are not integers. If we restrict ourselves in the system of integers, that's what we do when we are saying Diophantine equation, then this has no solution. Do you see why? It's really easy to see, given that we have already seen that 2x equal to 3 equation. You see, if a solution exists in the integers, that is x and y, such integers exist for which this is equal to this, then the left hand side is an even integer, again just like that 2x equal to 3 case, but the right hand side is odd, so that's why that is not a possibility. In fact, that's what the author writes. LHS is even, but the RHS is odd if an integer solution exists. So faced with this, it is reasonable to inquire about the circumstances under which a solution would first of all exist. So that is the first thing we have to do. What is the condition under which a solution would exist? And preferably that condition should be necessary and sufficient, in the sense that if that condition is met, then a solution would exist. Conversely, if a solution exists, then that condition should be true. And it's rather easy to find that condition. Let's see how. I can in fact write the statement here itself. Let ax plus by equal to c be a Diophantine equation where first we have to mention that a, b and c are integers. A, b, c are integers and a, b are not both 0. Because if a and b are both 0, then the left hand side is equal to 0 irrespective of x and y. They can be anything, and hence the right hand side also has to be 0. So in that case, we just simply have 0x plus 0y equal to 0, which is also an equation that there is no problem with that being an equation. It is an equation, but every every possible pair of integers is a solution. So it's a trivial situation. So to avoid that situation, we put this condition, this restriction, that a and b are not both 0. They are not simultaneously 0. One of them can be 0, leading us to that type of equations like 2x equal to 3. Okay. Then ax plus by equal to c as a solution. As a solution means two things. Okay, a solution means a pair x comma y, that is one thing, and because we are talking about Diophantine equations, that pair should be a pair of integers. In that sense, as a solution, if and only if d divides c, where d is the greatest common divisor of a and b. And now looking at this condition, so this is the necessary and sufficient condition for the equation to have a solution, integer solution. So now looking at this condition, you can now realize why this is the fourth section in this chapter. That's because GCDs are involved, greatest common divisors are involved. Now how can we prove this? Let's see. Assume that, note one more thing, that because it's given a and b are not both 0, so from the theory of GCD we know that their greatest common divisor exists. Okay, because in GCD also we need this condition. One of them can of course be 0, then the other has to be non-zero. Now assume that x equal to x naught, comma y equal to y naught, be a solution. That means it has a solution. And these are integers. We are not going to mention this fact again and again. Is a solution is and not are because they constitute a single solution. Is a solution to ax plus by equal to c. That is ax naught plus by naught equal to c. Now, because D is the GCD of A and B, so that means D divides both A and B by definition. So A would be some multiple of D, B also would be some multiple of D. For some integers R and S, and this line is of course independent of this assumption. In fact, I should have written it before writing this assumption, but anyway, you understand what we are doing here. Hence, C equal to, so now C becomes what? In place of A we can put dr, so we have dr x naught. In place of B we can put ds, that is equal to d times r x naught plus s y naught. This implies D divides C. But hold on, not so fast. How? The reason D divides C is because there are two things to note here. One is that R x naught S y naught, these are all integers. So this combination R x naught plus S y naught is an integer. Fine. So C is a multiple of D with this integer. Is that enough to say, by itself enough to say that D divides C? No, we also need D to itself be non-zero. Otherwise, division is meaningless. But D is non-zero. Why? Because D is the GCD of A and B. So by definition, D is not just non-zero. D in fact is a positive integer. Whatever it is never equal to 0. It is also not negative. So that's why now we can conclude from this equation that D divides C. But this is only one half of the claim. Conversely, let D divide C. That means C is some integer multiple of D. Let T times D, where T is an integer. Okay. Now we have to use a fact that we already know about GCDs, namely that the GCD of A and B is a linear combination of A and B with integer coefficients, and very nicely that fact would immediately lead us to the equation ax plus by equal to c. Now we know that there exists integers, what should I call them? Let us call them n and m. We don't have any n and m here, no? Such that and if you run out of this type of names, you can always use Greek letters. Anyway, we are talking about Diophantus, so everything is Greek, such that D is equal to NA plus MD. Now what we do, we multiply throughout by T, because TD will give us C, that is C equal to TD, which from this equation becomes TNA plus TMB. Hence the given Diophantine equation has a solution, and that solution is x equal to Tn and y equal to Tn. Pretty neat this whole thing is. So that means we have been able to show that that condition is in fact an equivalent condition for the equation to be solvable. However, there is a more general result. So this is only about the equation being solvable, that is one thing. But what is the next natural question? When it is solvable, what is not just one root, one solution, but in fact what are all the solutions? So to answer that, here is this next theorem. So we are going to state this theorem, half of which we have proved here, and the other half we are going to prove in the next video. So the theorem goes like this. The linear, of course, because we are considering linear differential, I said differential equation, Diophantine equation. The linear Diophantine equation, differential equations also I will start at some point. We will see linear Diophantine equation ax plus by equal to c, where a, b, c are integers and a, b are not both 0, has a solution if and only if, this part of course is just we are again writing what we have already seen a few moments ago, but the extra thing in this statement is going to be an expression for all the solutions, not just the condition for solvability. If and only if D divides C, where D is the greatest common divisor of A and B, and the rest is phrased like this: if x naught comma y naught is any particular solution, then all the solutions are given by these expressions: x equal to x naught plus b divided by d times t, and y equal to y naught minus a divided by d times t, where t is an arbitrary integer. So what this second part means is that say this condition D dividing C is true, so that there is at least one solution. Now if you, so that means there you will find some solution. It does not matter how you find. Okay, so that's a different thing altogether. How to find a specific solution in which you will find x and y, but I hope you can already guess how to do that. You just think about that procedure in which we express the GCD of two given integers as a linear combination of those integers. From that process, automatically solutions can be generated. You can pretty much understand, even if vaguely, how that works, given that you have already gone through that GCD thing in Euclidean algorithm. Okay, but say that way you have found a solution x naught comma y naught. Now what are all the solutions? All the solutions look like this, where the x part looks like this: x naught plus b divided by d times t, and y looks like this: y naught minus a divided by d times t, where t is an arbitrary integer. Is t given to be no, t is not positive, nothing like that is given. T is any integer. Okay, so you can see one or two things from this expression itself. Note that this, so what is the claim in this second part? The claim is that any solution to the actual Diophantine equation looks like this. That means as you are varying t over the set of integers, you are going to get all the solutions. That's what this entire thing means. In particular, if you put t equal to 0, you get that specific solution back, where x is x naught and y is y naught. One more thing you can notice is that If you write minus here and plus here, still there is no problem. Why? Because you can replace t by minus t. No, t is any integer, so as t varies over the set of integers, so does minus t. So you can, in fact, if you want, you write minus here and plus here. However, do not write both plus here as well as plus here, because that would mess things up. So that means in proving this second part, what do we have to prove? We have to prove two things. One is that this pair, that is this two expressions, if you substitute for x and y, this expression in the equation, then the equation is actually satisfied. That is rather easy. But there is another thing you have to prove, is that if you are given an arbitrary solution, say x prime, y prime, you then have to prove that that x prime looks like this and that y prime looks like this for some t, to show that in this list of solutions we have accounted for all the possible solutions. So we will see that in the next number theory update. And the next upload is of course on Friday, and that is again going to be graph theory. So that's just it. I end this video here itself for tonight. If you want to say something, you can write in the comment section below, or you can mail me at my address. The link will be there in the description. So see you on Friday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.